Okay, here we're going to solve the second part of the flood frequency analysis practice problem using data from Henry's Fork River, but this time we're going to use the complete data set from 1913 to 2015, which is over 100 years of data. And you'll see that we're going to get quite different answers for the 50, 100, and 500 year predicted flood discharge. In addition, we're also going to consider the 50, 100, and 500 year flood stage because I'm also including on this spreadsheet the stage data, the stage measurements that were made at the same time discharge measurements were made for that time period. And if we go through the data here, I've opened the spreadsheet, you'll see that there are some years when I've got gaps in data. For example, there's no stage measured in 1989. I don't know why, maybe something was broken, but this is not uncommon that we may not have complete stage data. That doesn't really matter as it turns out, so we're still going to be able to plot a rating curve and fit a curve to the rating curve and do our problem. So once again, the problem, our goal here is to calculate the 50, 100, and 500 year flood discharge and stage for this river. And we're going to go about it exactly the same way we did before. The big difference here compared to the previous problem is that we have a lot more data. And this is going to make it actually just a slightly more difficult in Excel. The fact that it's just slightly more difficult, not much more difficult, is a tribute to the power of Excel. So first thing we're going to do, as always, is we're going to sort our data by discharge. So I'm going to grab all the data here and I'm going to sort them. We'll take off the headers here. So we're going to sort by column B. That's discharge here from largest to smallest. And there we go. And then I'm going to rank them. There's my rank in column D. So the largest is ranked number 1, and 2, 3. I guess like those can be. And then I want to just extend that all the way down, grab hold of that, and pull it all the way down to the bottom. There we go. So we have 103 years of data. Next step is to estimate the return period in years. And that formula is going to be n plus 1. Remember what n was. We should take another look here. It was 103. So we have 104 divided by the rank in D2. And so I'm now going to copy this all the way down. And there we have our data. Exactly the same thing. We want to copy this column here so that we can plot easily. Insert copied cells. There they are. And now we're just going to plot the return period versus the discharge. And this is going to be a lot more data. So let's see what we get here. There we go. Okay, and now the first thing that should become apparent here is that we have a rogue data point, an anomalous data point. This one, number 1, the largest discharge, the largest stage, it's way outside of the range of everything else. Now, how we deal with that, we're going to have to think about that in a second. But let's just go through the procedure of what we would normally do. We're first going to change this x-axis to logarithmic. Okay. Boy, now, oops, that doesn't look very good, right? So I mean, the data look like they're defining a trend for most of the trend. There's a little hook on the end, but this data point up here is way out in space. And you know, sometimes this is what you're going to be faced with. You're going to have some kind of rogue data, and you have reason to believe, based on everything else you see, that there might be something wrong with this. Perhaps at this enormous discharge, it was very difficult to measure the stage, or maybe it was enormously difficult to measure the discharge. But for whatever reason, it does not appear to be even related to this data set. And so I'm going to do something that we have to do sometimes, is I'm just going to ignore it. I'm just going to pretend that that data is unreliable, and I'm going to get rid of it all. Just going to delete it out. Now, to delete it out, I really should recalculate my rank here now. So the largest now was the second largest. So I'm going to recalculate these ranks. Just drag these all the way to the bottom here. And luckily, I'm not going to need to do much else. Notice now that I have only 102 years of data. I got rid of one of them. And so this formula should be 103, right? Because it's n plus 1. So I'm getting rid of that data point, just pretending it didn't happen because I don't trust it. And I just recalculated, and there we go. So these are my new improved data, let's just say, without that one rogue data point, and it actually doesn't look too bad. But what happens now when I try to fit a trend line here? So I'm going to try to fit my logarithmic trend line, and you notice that It doesn't look very good, especially near low values of the return period or the discharge. And this is actually fairly common with large data sets in that they have, there's the upper part of it seems kind of linear, and then there's sort of a hook that occurs at the bottom. This is actually something that's an artifact of how we're doing this, plotting this simply as the logarithm of the return period instead of a more sophisticated statistical analysis. But there's a way I can show you to sort of get around this problem if you're going to do that. And that is to sort of ignore these data where the hook lie at low values of the return period, because really we're interested mostly in extrapolating this to higher values of the return period. So we're not really interested as much in what happens at low values of the return period. We want to preserve the trend that exists from the medium to the high values of the return period. So the way I'm going to do that is I'm going to redefine a subset of the data that only include the linear portion of it. If we look here, that looks like that starts about 7,000 or maybe let's say 7,000 CFS. So if I go here and highlight the data that extend from 7,000 CFS on up, this data here, I'll color them red here. I'll give them a red part. Those data should be more or less linear. And I'm going to use them then to extrapolate the higher values of the return period. So I'm going to get rid of this trend line, and I want to actually add or overlay selected data on top of this. So I'll show you how to do that here. I'm going to highlight these data, and I'm going to now select data. So this is my data set. This series 1 is the data that I've plotted. I want to add a series. I want to add something that I'm going to plot on top of these. I'm going to call this the linear portion. And I'm going to manually define the X and Y values that I want to plot. And they are the values in red. So my X value will be the return period that's in red here, right? And the Y values will be the peak discharges that I've highlighted in red, those that are greater than or equal to 7,000 cubic feet per second. So there we go. And I say, okay, and go back up. And now you can see that in orange, this is the selected data. These are the linear portion of the data. And these are the data that I want to fit the curve through. This is ignoring that hook on the end. So when I'm going to right click on this and add a trend line, I'm going to add my logarithmic trend line, and look how well that fits the data. That's actually much more confidence inspiring than what I had before. Now, once again, I want to do two things. I want to extrapolate this data. I'm at about 100 years, so I want to extrapolate it forward 400 years, okay, to get to 500 years. And I want to display my equation on the chart. And there is my equation on the chart. And I'm going to make it a little bigger so it's easier to see. Okay, so I've done the first part of my problem, and now I can go down here. Let's actually make this a little smaller so that I can leave space here. And for return periods of 50, 100, and 500 years, I want to predict, using this equation that I've shown for the orange data, the 50, 100, and 500 year return period, discharges for those return periods. So this is the return period. Oops. Hit the wrong button and everything went to hell. Okay, so I want the return periods of 50, 100, and 500 years, and I want to estimate the discharges at those. And I'm going to do that by simply plugging into this equation that I've just written on, that I've just had Excel display on my graph. So it's equal to 62617.2 times the natural log of H21 plus 5020. There we go. And I'm now going to copy that equation down, and I'm done with the first part of my problem. So there are the predicted discharges, and you will note if you refer back to the calculations we did for the much more recent data set that these are very different than the conclusions I would have reached for just 15 years of data. And there might be two reasons for that. We probably should talk about that right now. One reason might be that 15 years of data were simply far too few to make those kinds of giant extrapolations to 50, 100, and 500 years. Certainly the 150-year discharges here aren't even extrapolations at all. They are falling within our data. So we should have a pretty good confidence for those. But the other reason that those data from the last 15 years might be different is that there might actually have been some fundamental change to the relationship between discharge and recurrence interval of the river. We might have changed it via dams. We might have changed it via land use. There might actually be something that's physically changing that's causing the return period to actually change in recent years. And we don't really know which of those is true, and that would require additional analysis. But right now, we'll just note that they are very different. These three numbers here are very different than what we got when we did this analysis using just the last 15 years of data. Okay, now the second part of this analysis asks us to calculate not the discharge, the peak discharge predicted for 50, 100, and 500 years, but the peak stage. So we simply need to convert these discharges into stages, and of course we do that using a rating curve. And the rating curve we'll plot down here is going to be the graph of the discharge on the x-axis versus the stage on the y-axis. So those are the values shown in columns B and C. So I'm just going to grab hold of all of these and I'm going to plot them up. That's exactly how we want them, with the x-axis on the left and the y-axis on the right of the two columns we've highlighted. So I'm going to take those data and I'm going to insert a graph. This is going to be my rating curve, and there it is. It's going to lie right on top, and let's just make room for it down here. Oops, so that I can show it down here. Okay, there we go. Okay, now there are my data, and the first thing I should note is that they're pretty good. I mean, that defines some kind of trend. There's a fair amount of noise here in the middle, but honestly, that's not bad for a graph of stage versus discharge. That's not a crazy looking rating curve. That kind of makes sense. Our job is to just fit some kind of curve through it, and the problem is that there's no known relationship here. So we don't know what kind of curve we can fit through here. We're just going to try a bunch till we can find one that looks like maybe we believe it. So we're going to add a trend line here. And let's just actually do one thing. One thing I'm going to want to do is I'm going to want to extrapolate this forward. Well, remember we had the 500-year flood discharge was 21,000. The highest discharge here is about 6. We're going to want to at least extrapolate this forward 5,000. The reason I say that is so that I can sort of see what happens at the large values of discharge, whether or not this curve is going to predict the stage well at those high discharges. And you can see right now that the linear curve is a pretty terrible fit. If I try a power curve, that doesn't look terrible, though it does seem to overestimate the stage at both high and low discharges. It fits it pretty well in the middle, but not very well at high and low discharges. We can try a polynomial here, and that obviously doesn't work. Surprisingly, what's going to actually work best here is the logarithmic graph. Now, it doesn't always work best, but in this case, the logarithmic curve actually fits our data really well and seems to fit really nicely through the high values of discharge and stage, and that's what we want because we want to extrapolate this. So this logarithmic curve for our data right here seems to give the best fit to our data. And so I'm going to choose this one. I'm going to display the equation on the chart like I always do. I'm going to make it larger so that my old eyes can read it better. And there we go. So we're almost done here now. So this is now my relationship between discharge on the x-axis and stage on the y-axis. And so what we're going to do now is convert these discharges that I calculated in cells I, 21, 22, and 23. Those are the estimated peak discharges for the 50, 100, and 500-year flood stages. And I'm going to convert them to, flood discharges to stage. So I'm going to take this value in I, 21, and I'm going to use the equation that's on the rating curve graph. So it's equal to 3.418 times the natural log of, and I did it again, I, 21 minus 21.162. I'm just entering that equation. And I get about 11.8 feet. There it is in feet. So now I'm just going to copy this equation down. And there we go. Those are my estimated 50, 100-year, and 500-year river stages. Might be of more interest to me than discharge. If, for example, I live along the river and I want to know how high will the river get on average once every 500, 150 years, and that would help me decide whether I want to live there or how large I want to set my house off the ground or whatever. And there you go. So there I've solved the problem using a couple different techniques that you haven't seen before. We've used the rating curve to convert between stage and discharge, and this is about the most complicated kind of problem I'm going to expect you to be able to solve with Excel for flood frequency analysis.